Hello, everyone, and thank you for joining us today for our weekly webinar. We're excited to continue the Thrust B series with a presentation from Dr. Jim Smith at Princeton University. Thrust B focuses on innovative technological solutions using the data, models, and enhanced process understanding developed in Thrust A. These solutions include building to community scale resource recovery and reuse systems, hybrid centralized, decentralized water infrastructure systems, fit-for-purpose water systems, green infrastructure, sustainable urban drainage networks, and resilient floodplains. The complete Thrust B series schedule is also available on our website as well as our calendar, and we will continue to record each webinar and post to our YouTube channel. As always, a link to the video will be distributed as soon as it's available. Please be sure to tune in next week for a complimentary presentation from Dr. Brian Bledsoe at the University of Georgia as he discusses urban floodplains. And with that, I'm excited to introduce our presenter for today, Dr. Jim Smith. Jim is the William and Edna McAleer Professor of Engineering and Applied Science at Princeton University. Prior to joining Princeton in 1990, he was a research scientist at NOAA working on the radar hydrometeorology program of the National Weather Service. Smith received his PhD from the Department of Geography and Environmental Engineering at Johns Hopkins in 1980 and a BS in Mathematics from the University of Georgia in 1974. He was the DAAD Graduate Fellow at the University of Bonn and a Fulbright Postdoctoral Fellow at the Center for Mathematics and Computer Science in Amsterdam. And with that, I'm going to hand the controls over to Jim. Bear with us for just a moment while we transition.
There are three principal topics that I'm going to be talking about. The first topic is really part of the core methodology for rainfall flood frequency analysis, and it centers on a procedure called Stochastic Storm Transposition that revolves around analyses of high-resolution radar rainfall fields. The second topic that I'll deal with is urban rainfall climatology, and I'll focus on the differences in spatial distribution of rainfall over urban regions in general, and then thinking specifically about the urban areas that are the principal study regions for UN. There are two aspects of spatial heterogeneities of rainfall that are important. One is that in many settings we have natural gradients in rainfall that are associated with mountainous terrain or land water boundaries. Certainly in the Front Range area and the Sun Corridor area of Arizona, Los Angeles, those are important problems. Land water boundaries are important along much of the eastern seaboard of the United States and the large urban areas. So it's an important part of the urban rainfall story. The second piece of it is that urbanization can alter the climate, and it can alter it in important ways related to flood hazards. So we'll be looking at that as well. Finally, in going from rainfall frequency to flood frequency analyses, the intermediary is going to be urbanized hydrologic models, and what I'll focus on are some of the issues associated with urban modeling of flood response in ways that deal with space-time variability of rainfall as one of the fundamental topics. The techniques that we use for rainfall and flood frequency analysis again center on analyses of high-resolution radar rainfall fields, and the figure that I'm showing now presents rainfall frequency analyses for the Charlotte metropolitan area that are derived from the stochastic storm transposition method that Dan Wright developed. So the upper figures on the right, the uppermost figure shows rainfall frequency analysis for a point in Charlotte. It looks over a range of return intervals, and results are presented for different time windows: 1 hour, 3 hour, 6 hour, and 12 hours. And then the second figure shows similar analyses, but specifically for the 110 square kilometer Little Sugar Creek watershed. Little Sugar Creek drains the urban core of Charlotte, and so it's one of the most important urban areas in the Charlotte-Mecklenburg County region. So these are the way the results look. On the left, there are two summary climatologies of the radar rainfall fields. The upper left shows mean June, July, August rainfall derived from a 16-year record of radar rainfall analyses, where the spatial resolution is 1 kilometer and the time resolution is 15 minutes. Now, from these we derive a storm catalog of the 80 largest rainfall events, and they're specific to a particular drainage basin area and shape, and they're particular to the time period that is of interest. So this is the way the analysis procedures look at the end of the day. Just a quick summary of the way the procedure works. The basic notion is that we have this catalog of large rainfall events, and what I'm showing here are results that are for this 110 square kilometer Little Sugar Creek watershed, and you can see the outline of the watershed. And once we have the catalog of events, we just randomly select events from the catalog, and we transpose them randomly in the region. So you see observations basically showing the outline of heavy rainfall from a storm in June of 2006, and then it didn't actually pass over Little Sugar Creek, and a transposed version of the storm may in fact pass over Little Sugar Creek and create extreme rainfall. So we randomly select events from the catalog. We compute rainfall over the watershed for the transposed storm, and then we repeat it times to the point that we develop long records of annual maximum rainfall over the watershed. And those are the basic elements of computing rainfall frequency analysis that is geared to a particular watershed, and it draws on all the storms in a particular region. So it's a resampling method. It does a good job of reproducing the NOAA precipitation frequency analysis results where it should, and then it provides more flexibility in carrying out a range of analyses that we would like to carry out for assessing not just rainfall frequency, but flood frequency analysis. And effectively, if we have a good organized hydrologic model, then the flood frequency analysis comes for free because we select our storm events, we have very high spatial and temporal resolution of the rainfall, and we transform the rainfall into flood peak magnitudes using our hydrologic model. So Dan Wright carried out analyses of not just rainfall frequency for the Mecklenburg County watersheds, but flood frequency using GSSHA, an urbanized version of GSSHA, as the hydrologic model. So there are a variety of data sets that are needed to implement the hydrologic model, and we'll talk a little bit more about urbanizing models like GSSHA or KINEROS. The other point I'd like to note, so in the bottom left there are flood frequency results for Little Sugar Creek at 110 square kilometers and for Briar Creek at 48 square kilometers. Again, once we've developed our rainfall frequency method and catalog, flood frequency comes for free, and we can carry out analyses over any location within the drainage basin. So we can effectively develop flood frequency over the entire drainage network. Now, one important detail, Dan sorted out results separating events that include tropical cyclone floods and those that don't, and there are big differences. For Charlotte, the largest rain events during the period of record are from a collection of tropical cyclone events. And there's several points here. One is that for the procedures to provide appropriate rainfall and flood frequency results, you really do need to capture the range of flood generating mechanisms that are critical for the upper tail. The other important piece is that these methods really are going to be strongly dependent on rainfall properties from the largest events. But with those, and with a hydrologic, a good urbanized hydrologic model, you've got an effective tool of looking over a diverse urban region and assessing flood frequency. I'd also point out that the error analysis kind of comes for free in these analyses, and that we create multiple realizations of a particular rainfall record. Now, the urban hydrology is a piece that we've been working on for Charlotte and for a number of the other study regions. Joyce Sho and Marie Tang Feldhaus have been carrying out analyses in both Charlotte and in Baltimore, examining urban flood hydrology. The figure here just shows gauged watersheds in the Charlotte metropolitan area. There's an overview of urban land cover, and I'll leave it at a summary that there is very broad diversity in properties of urbanization over the Mecklenburg County region in North Carolina. The results on the right just show for this sample of watersheds differences in peak discharge, the distribution of peak discharge, and in lag time. There are wild differences in urban flood response, and there are important features that we need to be able to capture in our urban hydrologic models. Joyce, kind of following on some of Brianne Smith's work, has been looking at what would characterize as the spectrum of urban flood response. For these analyses, and in these figures, we're looking at maximum 12-hour rain rate or accumulation over the individual watersheds, and peak discharge on the left, and total runoff on the right. And therefore, 3 of the watersheds in Mecklenburg County, they happen to have very, very different flood response properties, and they are characteristic of the type of variability we see in examining flood response in urban areas. What we're looking to do is to translate this observational constraint on flood response into the key areas that we need to enhance in our urban hydrology models. Now, I just point to several areas that are important, particularly for watersheds in the eastern United States and urban areas. Urban soils, there are large differences in urban soil properties in Charlotte watersheds. There are striking contrast in the history of stormwater management that lead to properties of flood response that are difficult to characterize simply from kind of aggregate characterizations of urban properties like impervious fraction. In Charlotte, as in a number of urban watersheds, there are a number of features in floodplains that lead to pronounced attenuation of floodways. Bridge abutments are one of the most common examples, and they play an important role in flood response. Related to urban soils, there's a question as to whether antecedent soil moisture plays a response in urban, intensely urbanized watersheds. From an observational perspective, we can see that in Charlotte, the role of antecedent soil moisture decreases markedly with intensity of urbanization. And then finally, there are properties of rainfall variability in space and time that really play an important role, especially as we move up in scale from 1 square kilometer to 100 square kilometer. Storms moving down a watershed may lead to very different flood response than storms moving up a watershed. And again, these are properties of rainfall that are that come along for free with the stochastic storm transposition approach, where we're basing our analyses on observational, high-resolution observations of rainfall. Now, switching gears to urban rainfall climatology, for Charlotte, one of the things you may have noted in the rainfall analyses is that there was a northeastern maximum in rainfall. It's kind of typical of a lot of urban areas. It's particularly pronounced in the Baltimore metropolitan region. The figures on the left, the upper figure shows mean July rainfall, and there is almost a factor of 2 difference in rainfall northeast of the city versus rainfall that's southwest of the city. There's an even larger difference when you look at the fraction of days with heavy rainfall. Here looking at the frequency of events with more than 25 millimeters of rainfall a day. The upper right figure is sort of an odd one. It's looking at rainfall restricted to Baltimore City per se. And you may be able to see that. That's the gray line that is located kind of on the southwest end of that area of elevated rainfall. And the odd thing is the rainfall maximum, when you just restrict attention to the largest rainfall accumulations in Baltimore City, the maximum is actually significantly northeast of the city. So there are pronounced spatial heterogeneities in Baltimore. They're more pronounced even than in the Charlotte metropolitan area. And there are important features that we need to take into account in developing procedures based on stochastic storm transposition. Now here too, we're using long radar rainfall records, 1 square kilometer, 15 minutes again, 2000 to 2016. In addition to Charlotte and Baltimore, we developed comparable records for Denver and New York. For Phoenix, it's just a catalog because of the arid, semi-arid nature of the region. But we've captured high-resolution rainfall fields for Phoenix for all of the significant rain events there. So these are one way of looking at the climatology of extreme rainfall or of rainfall as it pertains to urban flooding. At the climatology of urban flooding can come directly from stream gauging observations. And I show some data from what I thought was the flashiest watershed in the conterminous United States, which is Moore's Run. It's located on the northeast boundary of Baltimore, so it's kind of in that area of elevated rainfall. And I use as a measure of flashiness the frequency of flood peaks that exceed a unit discharge of 1 cubic meter per second per square kilometer. So unit discharge is discharge divided by drainage area. 1 cubic meter per second per square kilometer in some watersheds has a return interval of approaching 100 years. In Moore's Run, it's closer to 1 month. Moore's Run is the quintessential early 20th century urbanized watershed. It has very rapid response times. It has hydrographs that are largely that are close to unfiltered versions of peak rain rates. So Moore's Run, it turns out, wasn't or isn't officially the flashiest watershed in the United States. Brianne Smith did a study of the flashiest watersheds using U.S. Geological Survey stream gauging observations, looking at more than 9,000 stream gauging stations with the same metric, the frequency of flood peaks that exceed 1 cubic meter per second per square kilometer. So Moore's Run wound up ranking 5th in the 9,000 or so stream gauges. One other stream gauge in the northeastern portion of Baltimore, West Branch Herring Run, is number 9. Baltimore doesn't even get flashiest city. That goes to St. Louis for the top 10 are in St. Louis. You can't see them in the figure. There's just one big red dot there. That actually relates to 4 stations that have frequencies more than 10 per year for one's CMS per square kilometer of flood peaks. So Moore's Run and watersheds in northeastern Baltimore are indeed among the flashiest in the United States. One of the characteristics of urban flooding, and it's important to note that in looking at these flashy watersheds from the 9,000 plus USGS stream gauging stations, what you basically find are urban watersheds. There are a few others. There's some oddities in the Pacific Northwest, but you're largely looking at urban watersheds. And the other thing that you're largely looking at is thunderstorms. So in the top figure here, it shows the frequency of flood peaks that are due to thunderstorms. These analyses are based on cloud-to-ground lightning observations from the National Lightning Detection Network. And what we see is that certainly north of 70%, and for many areas more than urban areas, more than 90% of flood peaks are due to thunderstorms. Now, as we go to the southeastern United States, Atlanta in particular, we see that tropical cyclones. Now, this continues over into North Carolina and Charlotte, where there is significant representation from tropical cyclones in the flood record. And here, the tropical cyclone analyses are based on the HRDAT track data that the National Hurricane Center maintains. So in looking at urban flooding, we are principally looking at thunderstorms for the U.S. east of the Rocky Mountains, and to some extent at tropical cyclones in the south. Eastern United States. In looking at thunderstorms and thinking about how urbanization alters rainfall properties, the question for extreme flood-producing storms is, what is the role of the city itself in altering the storms? The figure here shows radar activity observations over about a 15-minute period for the storm that produced the record flood peak in Moore's Run in June of 2003. Yellow colors here, reflectivity values greater than 50 dBc. Those are high rain rates. This is a really intense mean line of storm cells that pass over the area. The figures, and looking immediately over Moore's Run, what the figures here show is the vertical structure of the storms that passed over Moore's Run. And so the vertical extent here goes up to 18 kilometers, and what we see in the green colors is we have storms that are more than 14 kilometers above mean sea level in their ecotop height. The gray colors are reflectivity values larger than 70 dBz. That would be golf ball sized hail that's more than 8 kilometers above the ground. And what we see over this 15-minute time period is that this thunderstorm collapses. And it collapses right over Moore's Run, and it produces extreme rain rates. Now, is that an important part of the climatology of extreme rainfall? In Moore's Run and West Branch Herring Run, one of the other flashy watersheds, is just a little to the northwest of Moore's Run. Brienne looked at storm properties with the 30 largest flood peaks in Moore's Run. The figure again shows that if you look at flood peaks in Moore's Run, the rainfall maximum has been in Moore's Run. Again, it's northeast Moore's Run. On the left figure shows property storms that pass over Moore's Run, with time 0 being the time of peak flooding in Moore's Run. And so there's height of the maximum reflectivity, there's ecotop height, there is a maximum reflectivity. And what we see is that it's a collapsing storm. And from looking at a collection of the largest flood peaks, what Brienne was able to do is show that, in fact, that is a characteristic that more than half the storms that produce flood peaks in Moore's Run reflect. And so collapsing storm cells and changes in storm properties as the storm moves over the city into the northeast are important parts of the climatology. Now, we've also looked at extreme rainfall through numerical studies, weather research and forecasting model. And so we're looking at how land surface heterogeneities affect the evolution of thunderstorms. The results here for a system from the upper left, we show observations of rainfall and then results with 4 different representations of land surface heterogeneity, including results in which urbanization is not included, and one in which the Chesapeake Bay is actually turned into grassland. Okay, so the basic story here is that there are systematic properties of storms that pass over Baltimore and produce flooding in urban watersheds in Baltimore that are tied to the spatial heterogeneities that we were looking at earlier in terms of rainfall. And we've been examining these properties of storms through numerical modeling studies using the weather research and forecasting model. The figure that we're looking at here shows results in the upper left-hand corner are observations, and then there are a series of simulations in which we change the representation of spatial heterogeneity in the land surface. So it's these types of numerical experiments that we've been carrying out to examine the role of urbanization in determining the climatology of extreme rainfall in the study region. And there, one of the main stories is that it's not just urbanization and the urban heat island circulation, but it's the interaction of the urban heat island circulation with the Bay breeze circulation. And the Chesapeake Bay and the Bay breeze circulation is really a bigger deal in terms of the rainfall climatology. And what the urban heat island circulation does is it changes the locations that are the preferred sites for thunderstorms to grow and to decay in association with the Bay breeze circulation. Now, developing an understanding of why rainfall varies over the study region is important in its own right, but ultimately what we're trying to get at is how we can develop procedures that use these resampling methods that are based on high-resolution rainfall observations over a region, but where we use the observations in a way that accounts for the very pronounced spatial gradients in rainfall that we were seeing over the Baltimore Metropolitan region, for example, and that will be even more pronounced when we look at Denver or Phoenix or Tucson or Los Angeles. So we've been focusing on developing tools for rainfall and flood frequency analysis in Baltimore in which we try to explicitly account for these spatial heterogeneities. In Baltimore, our focus has been Dead Run, which is a watershed on the western margin of the city,
Dead Run is a watershed that's been examined extensively in a number of studies, and so we know quite a bit about the flood hydrology of Dead Run. Now, the two basic elements that Joyce Joe developed for the stochastic storm transposition method for Baltimore is first a resampling technique that reproduces the spatial frequency of occurrence of events, and the figure on the left shows all the events that go into a catalog for 3-hour rainfall for a Dead Run shaped watershed. And then the second element is just a bias correction of the rainfall to reproduce the mean rainfall in the storm catalog over the study region, which is shown in the right. So it's a simple approach to try and account for the types of spatial heterogeneities that are important properties of the urban flooding story for the Baltimore Metropolitan region. The procedures, the figure here shows the rainfall frequency for Dead Run at 3-hour time period, and it compares it with the NOAA frequency analysis. Now, one of the elements to keep in mind here is that the NOAA frequency analysis is based on relatively sparse rain gauge observations, so it's not going to reflect the types of spatial heterogeneity that we think or that we have seen are important elements of the Baltimore Metropolitan region. So we compare with the NOAA frequency analysis results, but it's not going to be a sufficient way of demonstrating that we've captured rainfall frequency accurately. Now again, we're ultimately interested in flood frequency analysis, and so Joyce took Brienne Smith's urbanized GSSHA model for Dead Run with the stochastic storm transposition procedure, and the figures on the left show the flood frequency results. The bottom figure is for the outlet at 14 square kilometers at the Franklintown stream gauging station. And so we have results for 10, 100, 200, and 500 year time period. The variability due to the fact that we create a number of samples of flood records for Franklintown. And again, this notion that the error characterization kind of comes for free. The upper figure shows results for 5 subbasins within Dead Run. They're shown on the figure on the right. And again, the notion that we can look at flood frequency not just at the basin outlet, but we can look at it over the entire drainage network of the watershed. Now, what I'd like to end with are just some glimpses at other analyses that we're carrying out, both for other regions and looking at other aspects of urban rainfall. For the Front Range of the Rocky Mountains, we've been looking at the hydroclimatology of extreme rainfall. We've been doing it through our analyses of rainfall from high-resolution radar fields, as shown in the upper left for the September 2013 Boulder storm, and for simulations using the weather research and forecasting model. We've also been carrying out analyses like Brienne did using stream gauging observations over the entire United States. And the Front Range of the Rocky Mountains crops out looking at measures of extreme floods as one of the really scary areas. And in the long list of really intense rain and flood events that the Front Range has experienced, the June 1965 storm and flooding stands out as one of the largest hazards that we'll have to deal with along the Front Range of the Rocky Mountains. So characterizations of the hydroclimatology of extreme rainfall and flooding, the very highest end, is one of the topics we've been pursuing for the Front Range region. As I indicated earlier, we've also been looking at Baltimore and Charlotte style analyses for the Sun Corridor region. First, the Phoenix study area. The upper left figure just summarizes the study region and shows some of the observational resources. More than 300 rain gauge stations in Maricopa County in the Phoenix metropolitan area play an important role. Urban flooding and urban flood hazards are kind of distinctive in Phoenix in that floods that originate in the north to south flowing rivers north of the city are major flood hazards for the city proper, particularly Cave Creek, Skunk Creek, and New River. And so we focused our analyses in the Phoenix metropolitan area on those areas. The figure on the bottom left shows a representation of the upper bounds through envelope curve analyses for the Maricopa County area. And what we see is one storm in August of 2014 really dominates the upper tail of flood peaks. Now, not just for Maricopa County, but for all of central Arizona. Hydrologic modeling analyses are particularly complex for these extreme events in this type of environment. And the upper right figure shows results using KINEROS at scales from about 10 square kilometers up to several hundred square kilometers. And then the bottom right figure shows the types of storm catalog analyses that go along with the Phoenix studies. Now, in the Phoenix metropolitan area, or the broader Sun Corridor region, we've been examining the climatology of extreme rainfall, and one of here too, working principally with numerical experiments using the weather research and forecasting model. We've taken this August 2014 storm as a template for some of the worst elements of rainfall for the Sun Corridor region. And we've looked at numerical experiments that reflect the types of things that could happen to these storms in a warming climate. And so the results on the bottom left show experiments that are essentially looking at perturbing the water vapor content. Long Yang has carried out these studies along with the flood frequency studies that I was showing before. One of the messages from these studies, on the one hand, the figures on the right show that we can do a good job of reproducing the key storm properties in the current environment. As we perturb moisture, one of the things that we find is that we change all aspects of storm properties, and we don't see a systematic change in rainfall magnitudes. Structure and evolution of storms change dramatically with changing water vapor content. So the types of analyses that we would think about carrying out to look at how these storms would behave in a warming environment are going to be complicated by the response of these types of systems to increase water vapor content. Now, we also are looking at developing very high quality, high resolution rainfall products from the new generation of measurements that are made with the National Radar Network in 2012. The radar network was upgraded to make polarimetric measurements. These show, in addition to reflectivity on the upper left, we have polarimetric measurements that include differential reflectivity and differential phase in the upper right. These should allow for much improved estimates of rainfall at finer spatial and temporal resolution. So we're looking to get to several minutes in some cases, and certainly spatial resolutions finer than 1 kilometer, down to around half a kilometer for Phoenix, for Tucson, Baltimore, and some of the other study regions. Tom and Yoga and Tim and Brian have been looking at flooding in Tucson. This is one of the storms that they've been working with, and so we should be able to provide very high time resolution, very high spatial resolution rainfall analyses to go along with the hydrologic modeling studies. So that's the range of analyses that we've been carrying out, looking at hydrology, hydrometeorology, and hydroclimatology of flooding. At the end of the talk here, I've gathered the sort of current work that we're carrying out, some of it in preparation. If you're interested in seeing details on some of the analyses that haven't appeared yet, just get in touch, and I can send pretty finished manuscripts for most of these, and then a collection of the preceding analyses that tie into this work. So with that, I'd be happy to answer any questions.
So we do have a question. Could you talk more about the methods for the first stochastic rainfall method?
The figure up here. So the fundamental notion is that we're going to do rainfall frequency for a particular location, not just using observations for that location, because storms may have occurred in the adjacent region that are quite relevant to rainfall magnitudes in the area that we're interested in. But it's simply the small sampling area hasn't allowed us to see the full range of storms. So with stochastic storm transposition, the fundamental notion is that we use all of the storms over a region, and we use a resampling method to create a pseudo record for a particular location. So with the Charlotte analyses, we wouldn't just look at rainfall measurements over Little Sugar Creek. We would look at the surrounding areas and transpose those storms into Little Sugar Creek by this resampling and transposition set of analyses. So it's fundamentally tied to this notion of trading space for time and developing analyses of how extreme things can get at a particular location. The challenge that we've been wrestling with is that as you expand the area, you run into more problems with the rainfall records not being representative of the precise location that you're interested in. So spatial heterogeneities are a really big deal in developing and implementing these procedures.
Okay, and kind of dovetailing on that question, she's wondering, how do you select the boundaries of the region?
Yeah, the boundaries of the region, in the case of the Charlotte metropolitan area, there are spatial gradients that are associated with the central Appalachians that are to the northwest. And so it's a compromise between expanding the area and keeping the kind of rainfall regime one that is directly relevant to the Charlotte metropolitan area. For Baltimore, it gets even more problematic, and because there are larger spatial heterogeneities, and so there we try to minimize the selection of the precise boundaries by having a procedure in which we reproduce the spatial frequency with which storms occur in the region, and we reproduce the climatology of mean rainfall over the region. And that's that's this notion of not just sweeping the spatial heterogeneity under the rug, but trying to directly attack it.
Okay, well, we've got a couple more questions. Alan is wondering, what is the current thinking about the mechanisms of urban influences on rainfall?
Current thinking of urban mechanisms. Certainly the urban sea island circulation is well recognized as an important part of the climatology of urban areas. The real question comes into play is how it interacts with the storms that produce extreme rainfall. In the Baltimore region, as in a lot of the U.S. east of the Rocky Mountains, the storm systems are characterized by a weather system approaching from the west. It's typically a trough, and so winds are blowing from southwest to northeast in many cases, and that's why we see this northeastern maximum in rainfall in a lot of settings. And so what we try to understand is how the ambient environment of storms interacts with, first, the urban heat island circulation, secondly, with the changed roughness associated with the urban area. So tall buildings impart more drag on the lower atmosphere than the natural environment. And then finally, the aerosol distribution in urban areas can be different from the ambient environment, and that also has an impact on storms. And so I think the key element is tying in ambient environment of storms with how principally roughness and urban heat island circulations affect evolution of storms.
Okay, and then we have one final question. I'm going to try and unmute Zhang Zhang to see if he or she can answer or ask this directly. Hey, Zhang Zhang, you there? Nope. I think I failed. Okay, well, I'm going to repeat the question, and hopefully you'll understand. So, with consideration of the spatial heterogeneity, how did you consider the storm characteristics like intensity and occurrence probability when it's transposed?
Yeah. We did it in the simplest possible way. We knew the climatology of the storm catalog, so we have the spatial rate of occurrence. And then for a particular storm that we're looking to transpose, we know its location and its magnitude. And so the two things that we did is in picking a storm, we chose location so that we reproduce spatial rate of occurrence, and then we modified the magnitudes of rainfall systematically so that we maintained the mean rainfall for events in the catalog as a function of spatial location. So the method doesn't directly account for any of the things that we've learned about how urbanization alters storms. And we look to make that transition, but now we've got ad hoc procedures that take us the next step in dealing with urban impacts on rainfall.
All right, great. Well, I haven't seen any new questions pop in, so I appreciate your time today, Jim, and thanks again to everybody for tuning in. I'll be sure to send out the link once it's posted on YouTube, and stop back next week when Dr. Brian Bledsoe gives kind of a complimentary presentation to Jim's discussion today. Have a great day, everybody.